So Keysight Technologies is the world's largest test and measurement manufacturer for electronic equipment. So you may be wondering why on earth we're here. Our role is to help design, verify, and test those 28.1 billion devices you're going to see by 2020. So we're kind of at the pointy end where the rubber meets the road. So we're primarily an electronics company, but very much focused on the IoT side. And that's the evolving attack surface you see, a highly connected city with all sorts of power infrastructure, water infrastructure, you name it, connected devices. And this is seen as the next great attack surface, effectively. And if you go to the Senate Armed Service Committee, which have got a budget larger than GDP of some countries, of all the terrible things that are going on in the world at the moment, job one for the Department of Defense is our highly connected societies and the vulnerabilities within them. Particularly those devices designed and tested and fielded with minimal requirements and testing, and also the complexity of those networks. So the thesis is that our current sort of perimeter-based approaches won't address these devices. You can't really put a virus scanner on something that's a wearable device, for example. How do you do a pop-up in a kettle? It doesn't happen. So we have to sort of rethink how we interact with those devices, and more importantly, how to make those devices secure by default. So that's kind of driving us, and that's why Keysight's getting drawn into this, trying to make things, design security into devices. So who cares? Probably not for consumer devices, but there are three groups that do care about it. Anybody that's designing stuff for critical infrastructure protection, stuff that's going into the aerospace defense chain, stuff that's going into critical infrastructure, you need to make sure there's a resilient communication and transport infrastructure there. You also need to assess your supply chain as well, because very often we're finding things like counterfeit parts coming into the supply chain, counterfeit software, malware pre-delivered in stuff that's getting integrated in large devices. So anything that finds its way into the infrastructure supply chain is a potential risk and a potential threat vector. Other people that care about it are law enforcement and threat intelligence. We've already heard about how the bad guys are using strong encryption and devices to put stuff in. The amount of digital equipment that's getting seized is growing phenomenally. There were 30,000 devices seized by the Met alone last year as part of evidence gathering. And within a typical case, there's about 7 devices that are seized. These all have to be analyzed. And they're increasingly complex, they're increasingly using very sophisticated encryption. Then you have to protect the safety of people that are actually using the net as well. And the last people that are concerned about the information assurance standards bodies, we're seeing a rise in, which is a good thing, of testable requirements for equipment that's going in for infrastructure, also things that are going to get deployed. So Underwriters Lab, for example, provides a standard for cybersecurity of embedded devices. So we're starting to see testable requirements coming into the industry, and then we're also trying to derive those into things like healthcare, telecommunications as well. So we need to sort of drive those standards. So the project that we are working on in conjunction with Professor Buchanan and Napier is something we call bare metal forensics. So what we're doing is trying to bring back our test and measurement electronics history and link it up with the leading edge research that's going on inside the cyber community. Because I think you'll appreciate that even though I've, in my days when I've done computer science, we actually understand how a computer works. I don't think many computer science graduates would tell you how a computer works nowadays. We learn a lot how to use things and put things together and integrate it. So we've kind of lost that how a computer works, and we've really lost the heritage about the electronics. So we're trying to bring that back together, because by the same token, and people that are helping to design electronic equipment, they have to understand how cyber works as well. So there's exactly a symbiotic relationship going on. So the first area, the problem itself is that we've got these highly embedded and diverse connected devices. It's impossible to put a scanning agent in 64K of memory. You've got a supply chain that's very uncertain, so very often devices are baked in big foundries and then find their way into all sorts of things in specific applications. There's no compliance regime in place for electronics, really. And very often there's minimal testing. It's all about meeting market windows and costs. The costs involved in designing new electronic equipment are phenomenal. If you were going to do a system on a chip, for example, the mass cost and additional startup is about $280 million. So you have to sell $1 billion of equipment to design a new chip. So your only alternative is to take lots of old stuff and stick it all together. So what we aim to do with the bare metal forensics is to start to exploit the industry standard interconnects to get visibility inside those devices. There are also manufacturing test ports to test devices as you build them, and we're going to start exploiting those to control the execution on the device and check for vulnerabilities. And then the last area we're doing research with Napier is using precision analog measurements to detect side channel leakage. I'll explain a bit more about side channel coming up. So initially you would think cyber, that's all virtual. You've got these test and measurement guys doing the scopes with the wavy lines and their analog stuff. What's all that about? Well, there has to be a physical implementation that uses standard components. You actually have to build the thing. So there has to be a piece of things that you have to test. And then lastly, you will have observed phenomena from those devices. Physics takes hold, you know. It takes a certain amount of time to send things down a computer bus. There'll be electronic admissions, all those sort of things. So a virtual system doesn't exist in a vacuum. There is actually a physical implementation of it. Using test equipment, you can start spoofing that. So you can actually generate attacks at the electronic level. Then you can analyze the data that's happening inside the device as well. So nothing might be appearing in the operating system, but there's lots of stuff happening underneath the duct. And then the last thing you can do with those observed phenomena, you can measure it. So you can look at power variation, you can look at RF measurements as well. If you take those measurements and analyze them, that will allow you to infer the operation of the cyber system itself. So even if it truly is a black box, there'll be an electronic signature that's given off that you can start analyzing that. So here's an example of what the attack surface looks like. I've said before that there are these larger committees that set up standards for interconnecting devices. So if you were to rip apart a cell phone, you would find these devices. There'd be a system and a chip. There'd always be a GPS component. You know, there'd be sensors. There'd be touch screens. The way it's all glued together all uses standard buses. So actually inside your electronic device, it actually looks like a computer network itself. And those links that you see, they're actually exchanging protocols between the chips. So they actually talk to each other and there's defined protocols between them. Because of the large volumes in the electronic industry, these chips and interconnects find themselves into everything. So the IoT is an obvious example, but you know, the billion smartphones that are constructed a year ends up in those, ends up in wearables. There are probably about 50 microprocessors inside a connected car and interconnected buses in them, and then wearable devices as well. So if you can get insight into those, you can actually get insight into how things are operating. So here's an example of some of the stuff that we measure, and it's the sort of data analytics, the high-level analytics that we do inside our test equipment. Now, all these sort of look a lot of alphabet soup, but all these are interconnect standards. So things like CAN bus, for example, is the bus that runs through your car. So if you plug into the test board, there's a protocol that runs inside there, and you can see what's going on. So you can see the analog signal on the top there. Once you decode that, then things get interesting. You see you can read a fuel gauge, you can read out the airbag, for example. There's all sorts of information. If you inject stuff on that bus, you can cause things to happen. So you really need to verify that those internal interconnects are all secured. And you can see a lot of those standards as well are all potential ways of injecting stuff. For example, we've got things like I2C, which is the buses that use for sensors. So you can spoof all sorts of sensors, really. You know, power sensors, temperature sensors, you name it. Location sensors, you can spoof location. And then we've got the interconnects on the buses themselves. So if you want to read out stuff from the memory interface, you can see the stuff traveling across the bus and capture it. So again, the image on the chip itself might be inside the system on a chip, but you can see the data running through the buses and you can capture that. So we're talking about big data, and in terms of Keysight, we wouldn't claim that the big data is big in volume. We certainly do not do that. It's gigabytes. But But if you look at the IBM sort of model of the 4 V's of big data, we can certainly tick the velocity box, a high-end sampling scope, so 1.28 terabits per second in a single channel. So we can tick the velocity box, and those devices are about $400,000, so I can take orders afterwards. On terms of the veracity of the data, it's extremely noisy. Very often electronics runs right at the limits of physics, so it's very difficult to get an accurate trace, but when you can, there's a lot of information in. So data's noisy, it's partial, it's not predictable, and it's very difficult to get training data because it's highly proprietary. And then lastly, we've got the variety. That stack that you see in there is the stack that you will see on a single chip inside a cell phone. So there's about 10 standards there, and each of those standards has maybe about a dozen variations, depending on power, voltage, etc. So there's a huge variety of data, but that acts as a big data source, and the challenge is to analyze that. So Keysight have done this before. We actually done it this was actually looking at traces on a system on a chip. We're looking at the behavior that was coming out of a system on a chip, capturing a bus, and we got some small measurement traces. And what we've done was a full correlation on that, so what we're trying to do was fingerprint the execution of the devices. To actually do the cross-correlation took about 2 hours at the Edinburgh Parallel Compute Centre, so there's good resources locally in terms of big data analysis, so we basically hired the cores by the hour. And from that, we got a correlation matrix of all these different measurement traces. We took traces from devices that had malware, didn't have malware, or different strains on that, and then cross-correlated them. And then at the end, you get a behavioral network, so you can actually see there's different strains of malware, and you can group them together. So what you've effectively done is done an electronic fingerprint of the devices, and once you've understand what normality looks like, you can look for abnormalities, you can look for the outliers sitting out there. But that took a lot of work, and the data science wasn't quite there. So where we are now is that we are working directly with Napier University on the bare metal forensics project. And this is brokered by Data Lab, so they're helping to advance the data science aspects of that. So Keysight's turning to Napier to work with on the data analytics side of it, because they've got world-class cyber forensic research. They've got an accredited MSc, so you guys are already been treating for, security from the outset. So there's a lot that we can learn from Napier. They already have the public and private partnerships in place and can put on conferences like this and do the outreach. For our side of it, we have the electronics expertise. So again, we can learn from each other. And hopefully we'll be able to develop secure devices and build those tests into our equipment in the future. So one area that we can look at, and these slides are produced by Napier themselves, are looking at side channel attacks. And Napier introduced a side channel, says, did you know that inside a cryptographic system, there's a public key, there's a private key. You need to get access to a private key, perhaps in a security investigation, or you're looking to see if a banking device is going to leak information, is it a potential threat? Side channel means that there'll be a signature in the world of physics that gives off some indication of what the data is inside it. So it might be a power signature, it could be heat, it could be light, it could be a timing signature, it could be an RF emission. And from that, if you really push the analytics, you can start extracting information from the devices. In some cases, recover the secret key itself. So for example, this is some of our measurement science, and it's not come out too well, but these are different inputs. And if you look at the orange line, kind of looks like a wavy line. Now, this is actually looking at power rail of a device as it's doing cryptography. And there's too much noise in the top level, but when we turn the resolution up and get rid of the noise, then you can look at the green line and the bits in the white circles, there's very small peaks, and that's a signature that's actually doing cryptography, and it gives us a bit of a hint on how the cryptography works. So we're developing those techniques further to do it. And the project itself is looking at exploiting those side channels. So from our measurement hub, we're looking at, okay, what information can we get from mobile phones? Things like fingerprint sensors, are they vulnerable? Can you spoof those? Are the keys held inside the fingerprint sensor that we could get to so you don't have to put a fingerprint on it? So could you spoof biometrics? In terms of small embedded devices, are there already vulnerabilities in there? Can you observe the behavior so you don't have to do malware analysis, for example? Things like internet hubs, for example. Again, is there vulnerabilities? Is that an attack vector to get onto a home network and spoof things? And then lastly, sensors as well is an area that we're looking at. So this is a demonstration done by our colleague Owen Lowe, which is actually using our equipment. And what this is going to show is a very simple one. It's a security keypad. And very often these are done in microcontrollers. And as I say, these things are done in a hurry. They're not necessarily, the people that design this electronic equipment are not skilled in the tradecraft of security. So they make a lot of blunders. So in this small keypad, what we're looking at is the time it takes from putting stuff in on the keypad to the light going on saying, sorry, you've got the wrong key. So what Owen's actually been able to demonstrate is that by measuring the timing it takes from entering a key to the light going on, you can decide whether you've got the right number or the wrong number as it's going on the keypad. So if you fire this up, you can see that we are measuring the timing that's going on inside the microprocessor. And we're trying some numbers here. Oh, there's 7. Yeah, that looks better. So the software is actually working out the timing attack here. So we've got, okay, 7 is the right number. So let's try the next number, 7, 5. Let's try some more. 3. Oh, yep, 4. One more try. There we go, cracked it. So rather than setting in 10,000 numbers, by watching the behavior and saying, okay, we've got the right number, it's a bit like spinning the old bicycle locks. You used to be able to just jiggle them, find one that matched, then the next one, then the next one. So we've actually greatly reduced the search space on that just by looking at the electronic signature and crack that keypad in 13 tries rather than 10,000. So you can think of that in things like, okay, how do you unlock a phone potentially? Are there underlying signatures that you can look at that and unlock those? And they would be vulnerabilities that would have to be addressed in the device as you move forward. Oh. So in summary, insecure devices in the IoT will potentially spread vulnerabilities into critical infrastructure. They are the weakest link in the chain. There's lots and lots of good data analytics that you can do on the outside and the perimeters to help guard the data inside the cloud, etc. But it's a potential way in if you have purely designed devices. OS agent-based techniques don't address those devices. You can't get a virus scanner for a 64 kilobit system on a chip. It's just not going to happen. And you can't run large complex virus scanners even on handheld devices because you're going to end up flattening the battery. So there's a trade-off between convenience and usability. We can infer clues on the operation of the devices from these electronic measurement traces, and we're building on the data science research to develop those analytics to get to detect vulnerability from these traces so that it can effectively do a sweep of a device, look for vulnerabilities, either exploit it from an enforcement point of view, or to go back to the basics and say, let's design for security. You've got vulnerabilities, how do we address those? Or how do we test them and make sure things are happening? Okay. Yep. So.
So, any questions? Bare metal forensics. Yeah.
So if malware or something has kind of been brought in when the chip's being baked, what you bought a batch from somewhere, is it more difficult to obtain a fingerprint of what something should look like or should be when you're not certain about the source of the one of the chips that you've got in the device?
It can be, but very often a counterfeiter will look for a licensed device that's in has high degree of distribution, so you can usually get it. And there are very often you'll find they'll cut corners that things that don't make the speed bin, for example, rather than getting chucked in the bin, they find their way itself into another part of the supply chain. So there might be a safety vulnerability there, but not necessarily a bad piece of malware. So by doing electronic traces, you can see, okay, this signal isn't rising fast enough. It's obviously something that's knocked off. There are other things that, because all these devices have data sheets, you can usually do tests against the data sheets to find them. So that's one area. Malware is sometimes a bit trickier, particularly if it's got like an embedded bootloader or something like that, because very often these systems in a chip, they don't publish anything. All the specs are all in Chinese. So at that point there, it comes down to almost like unsupervised learning. You have to try and learn, get some good stuff and say, well, that just doesn't match. And then look at the variation and see what you have. But yeah, it can be quite difficult when you bring in things like bootloaders, for example.
Just as a follow-up as well, the amount of devices that that have been mentioned in 2 talks so far, I don't know how many billion it was by 2020, but that's quite a task to understand the fingerprint for each one of these that may or may not be used by a bank or a society or whatever.
Yeah.
So I'm sure you certify them or something. You kind of work to identify what's a good system, and say to a bank, yes, that's a good one to use. Or something.
Yeah. So you're absolutely right. You couldn't, 20 billion devices. You're never going to do it. And software releases coming out every 3 months. You're never going to do one for the entire one. The best you can probably do is to break down into a bill of materials on that part. Remember that we work closely with the chip manufacturers as well, because we're trying to do the test stuff. We sit on the standards committees where you're developing these traces as well. So we have a degree of inside knowledge about certain devices and what their fingerprints look like. They're highly proprietary, but we have knowledge of what they look like. Again, because we sit in the standards committee and we do compliance, we can do a basic compliance. So we know how close things are to the compliance, and then we can measure it. So we can always go back to the open standards from the IEEE or GDEC or somewhere like that and test against it. So you really have to sort of break the problem down a wee bit.
Thanks very much indeed. Please give a round of applause to Carson.